Hi, let me conclude the discussion of rational functions with some application problems. I've selected a couple from the textbook, problems 40 and 43, to review with you. Problem 40 deals with an environmental issue about recycling, and it talks about the cost for supplying bins to P% of the population is given by C is equal to 25,000 P divided by 100 minus P, where P is between 0 and 100. So the input is P%, the cost is our output. We're to find the cost of supplying bins to 15% of the population. Well, that tells us that our input value needs to be what? Yeah, 15. So on the calculator, we can input 25,000 times 15 in parentheses, divided by 100 minus 15 in parentheses, and see that the cost for supplying bins to 15% of the population is $4,411.76. The cost of supplying bins to 50% of the population, well, here the 50 represents our value of P, and so plugging in 50 in place of the P gives us 25,000 times 50 divided by 100 minus 50, so that cost would be 25,000. And then the cost of supplying bins to 90% of the population, P is equal to 90 in this case. Substituting in the 90 in place of the P gives us $225,000. Okay. Then it says to use a graphing utility to graph the cost function, choose an appropriate viewing window and explain why you chose the values that you used. Well, I've entered the function into the calculator, 25,000x in parentheses, divided by 100 minus x. I knew my range for the x min and x max because of this restriction on the input P was between 0 and 100, so that's why I let my x min and x max be this. Now the y min and y max, it wouldn't make sense to have a cost of $0, right? And then the y max, well, I just knew going through these three problems that I got up to 225,000 for 90%. So that's why I chose something slightly larger than that, which was 250,000. And I chose a y scale of 50,000. So my x-axis is going from 0 to 100, and my y-axis is going from 0 to 250,000. And there is a graph that you see in that particular part of the window. Now, according to the model, would it be possible to supply bins to 100% of the residents? Well, in this case, 100% would tell us that P would be equal to 100. But what is the problem with this rational function at 100? Right, it makes the denominator 0, so the value of P is equal to 100 makes the cost undefined. So it is not possible to supply bins to 100% of the residents. And another thing about this rational function, right, as we're getting closer and closer to 100, what's happening? Yeah, the cost is getting astronomical, so 95%, 99%, the cost is just simply going to increase. Now, the next problem deals with wildlife. It says the Game Commission introduces 100 deer into newly acquired state game lands. The population N of the herd is given by N equals 20 times 5 plus 3t, all over 1 plus 0.04t, where t is greater than or equal to 0, and t is time in years. It says to use a graphing utility to graph the model, find the populations when t is 5, 10, and 25, and determine the limiting size of the herd as time increases. Well, to graph it, you actually need to know some points that would be on the graph of this function. So I think these questions are a little bit out of order. It would make sense to find out what the population is in a few of those years so that you can use those as a guideline to set your window. And you can see that I have the function entered, and I've created or captured a few screens from the calculator here. I did the table so that I could see what the population is in 5, 10, and 25 years. So I started my table at 0 and I incremented by 5. So now in 5 years the population is 333, in 10 it is 500, and in 25 years it is 800. And if you scroll up and down in your table, you can see some values that would be a good guideline for you to use for that Y max. So I chose 0 to 50 for my X min and X max. I chose 50 just because of thinking about 50 years from now. And then my Y max I chose 2000 after looking at what these values in the Y column were doing. So in my graph, my x-axis is going from 0 to 50, and my y-axis is going from 0 to 2000. So we already know the populations at those three particular times. Then what about the limiting size of the herd as time increases? Well, as time increases, that is as t goes to infinity, we're thinking about what's happening to n. Well, that hopefully reminds you of the horizontal asymptote, right? We're looking at the long-term behavior. So as n or t goes to infinity, what's happening to that output? Well, to find the horizontal asymptote, we need to look at the degrees of the numerator and denominator and figure out which of the cases we're in. So let's rewrite this. First off, this is really 100 plus 60t divided by 1 plus 0.04t. So notice that the degrees of the numerator and denominator are equal. So that means that our horizontal asymptote occurs at the quotient of those leading coefficients. So y is equal to 60 over 0.04. And if I perform that calculation, I get 1500. So to answer this, what is the limiting size of the herd as time increases? Well, as t goes to infinity, n is going to 1500. So the limiting size of the herd is 1500. If you have any questions on the application problems, please contact me. Thanks.